The second fundamental theorem is a theorem that stems from the first fundamental theorem. So just to recall, the first fundamental theorem, so I'm going to write FTC, or we actually just called the fundamental theorem of calculus, said if I had an integral and I had an a and a b, f of, let's say, x dx, didn't we say that we could take this integral and then we could plug in, so let's say capital F was the answer to the integral. I could plug in b, and then I can plug in a and subtract these. Well, this was only true if a and b were constants, right? So as a reminder, only true if a and b are constants. Well, what we know is that we don't only work with constants in calculus, we also work with variables. So the second fundamental theorem of calculus takes a look at what happens if one of my limits does have a variable, and then continues on with taking a look at these derivatives of integrals. So what we're going to do is we are going to make sure that we are allowed to use the fundamental theorem of calculus, the second fundamental theorem of calculus, when I have a variable. So in this case, my general variable is x, and I have a constant. So just to keep note, c is a constant and must be the lower limit. So specifically, keep in mind that this is only allowed if my constant is at the bottom and my variable is at the top. Well, what ends up happening is I'm going to rewrite parts of these. So let's say I take this chunk right here. If I were to integrate f of t dt, let's call it capital F. Let's say that capital F is the antiderivative of little f, which actually means it's the answer. It's the answer that we would have gotten if we were to integrate this, right? So let's say I integrated this, and then what I notice is if I were to plug in, I would keep the d dx right here, d dx, and if I were to have integrated this, couldn't I call the answer capital F of t instead of little f? So capital F means I took the integral, and since I have limits, oops, sorry, that's a bracket. Since I have limits, I could actually say this is x and this is c. Isn't that true? That's typically what we do with the fundamental theorem of calculus. And then, to take it one step further, don't I plug in my upper limit and my lower limit? So I'm going to just keep this d dx and leave it there for now. But what we see is I would plug in capital F, and since I'm plugging in, instead of that t, my first one would be f of x minus capital F parentheses c. Oh, close parentheses right here. Well, what we notice is in this case, even though I've taken this integral, the next step is to take a derivative. So if I were to break this apart, don't I know the derivative of functions that have x's in them? So I can take this derivative. But in this case, we notice that no matter what, if c is a constant and I plug this in, once again, reminder, this is a constant, we know that the derivative of a constant is always equal to 0. So when I end up taking the derivative of the second part, this f of c actually cancels out. So what we end up getting is the derivative of the answer of the integral is actually back to the derivative. I'm sorry, to the integral, which was just f of x, little f of x. So what I would actually do is take this f of t that was in here and rewrite it, but plug in an x, minus the derivative of a constant is 0, just like we said, which means our final answer would just be f of x. So it's kind of like a ring around, but the one thing you have to do is you have to prove this and take the derivatives correctly. So let's go ahead and take a look at this example, and it says find f prime of the following function. So what I need to do is first, to find f prime of x, I need to write this out so I stick the derivative function in front of it. So I put the dx in front, and then in my brackets I put in my integral, -1 to x radical t cubed minus t dt. And so what we need to do is make sure that this matches our fundamental theorem of calculus. The first part is the d dx, which I have right here. I also have a function dt, and I have a constant in the bottom. So I'm going to type that out, constant. Right? My -1 is my constant, and I have to have an x on the top. So according to this, does this match the second fundamental theorem of calculus? Yes. So what I am allowed to do is just take my f of x, which was the inside right here, but instead of the t's, I can plug in an x. So my answer in this case would be the radical. Wherever I see a t, I plug in an x. So I get x cubed minus x. This right here is equal to my f prime of x. Good. So it's really a matching game, and if it matches, then we are allowed to use the rule. So let's go ahead and take a look at the next example. And I see I need to find f prime of x for this integral right here. So once again, I rewrite it, and I take the the derivative of both sides. So there's my derivative mark, is equal to dx bracket the integral of x pi over 3 cosine to the 5th t dt. And so I play my matching game, dt, sorry, that's a dt right there. Here's a d. Okay. So I play the matching game, and I see I have the derivative here. I have a function dt over here. Then I take a look at my limits. What I notice is, in this case, my x, in this case, my x is a lower limit, and my constant is up in the top. So let's think about how we can get this to match by using our properties. So let's write constant in at top. Constant is upper limit. In order to get this to match the second fundamental theorem exactly, I actually need the x to be my upper limit and the constant to be my bottom limit. So I go back and think about my different properties, and the one property that allows us to switch this is if I flip my limits. Well, in order to flip my limits, don't I have to make my answer negative? So what we end up doing is I keep everything the same, dx bracket, and if I flip my limits and I do pi over 3 at the bottom and x at the top, that means I need to stick a negative out front. And then I can continue with my cosine to the 5th t dt. That is allowed as long as I remember to put that negative out front. So according to this, does this now match the actual second fundamental theorem of calculus? Yes, my constant is at the bottom and my variable x is at the top. So now I plug in that x, and what I get is negative cosine to the 5th, and then I change that t into an x, and this right here is equal to f prime of x. Good. So if I can get them to match exactly, and I'm allowed to use different properties we've learned, then I can just plug into what's inside the integral. So let's take a look at how this problem is different. So it says simplify, and I want to find the derivative of this function. So I play the matching game, and I see that I have a d dx, I have a function inside, I have a constant in the bottom, it's exactly what I want, and then I do have a variable at the top, right? But the question is, does my variable match exactly what the theorem says? Not necessarily. I need x to be by itself, but in this case, this has a coefficient of 2. So what we're going to do is, first we're going to follow the rule. I'm going to stick this upper limit anytime I see t. So I'm allowed to say sine, and I get a parentheses. Here I see t, so I write 2x, and I need this to go into the third power, right? So technically, here's my derivative, but anytime I have a derivative with something in parentheses, don't I have to use the chain rule? So let me write this in. The chain rule must be used in this case because I don't have x by itself. My x is connected to this 2x. So what's the derivative of what's in parentheses? Well, that would be 2. So my final answer in this case would have to be, let's write in blue, 2 sine of parentheses 2 to the third is 8, x to the third is x to the third, and then I'm done. So as a reminder, chain rule must be used if upper limit is not x by itself. So what you pretty much will do is plug in the upper limit into your variable and then take the derivative of your upper limit. So let's go ahead and take a look at the next problem. Here we go. I have d dx, integral from x squared to 3, cube root of 8t plus t to the 4th dt. I line everything up again, and I have a d dx. I have a function in here, and then I have these limits. So there are two things that happen. First thing I notice is my constant is on the top. Constant. And then I also notice that my variable's on the bottom, but it's not just an x, it's actually an x squared. So what are the two things I need to do here? Variable. First thing is, I need to flip this, right? Because right now, I need the constant to be at the bottom. So I actually get dx parentheses negative integral, which allows me to move the 3 in the bottom, the x squared on the top, cube root of 8t, 8t plus t to the fourth dt. And the key thing is, since this is not an x by itself, I must use the chain rule. Chain. So I'm just going to write chain in here to remind us. Dang. Sorry. So this said chain. So now I am allowed to plug in this x squared, however I still need to use a chain rule. So the first thing is plug into the function. So I get cube root of, everywhere I see a t, I stick an x squared. So I get an 8x squared plus parentheses x squared to the fourth. And then I need to multiply by the derivative of the top. Oh, and I forgot that negative. Sorry, forgot that negative here. Derivative of x squared is 2x. So now if I simplify this, what we end up getting is negative 2x cube root, of 8x squared. And I have a power to a power, which means I can multiply those to give me x to the 8th. So you plug in your upper limit into your variable, and then you multiply by the derivative of the upper limit. So it sounds very similar to the chain rule, and that's exactly what you're doing, is using the chain rule to solve these. All right, good luck, and that is video 1 for second fundamental theorem of calculus.